evening. I'm Spot On Weather meteorologist Matthew Euler. Welcome to How the Weather Works training series, and this is part 5. Today we're going to be talking about atmospheric stability. It's a very important concept to really grasp as far as the type of clouds we see in the sky each day, whether we're going to see any type of precipitation for a particular day, as well as whether we're going to get any severe weather. So in general, atmospheric stability is a very important concept in meteorology. I'm just showing you a graphic here talking about some of the main things we look at when we want to talk about atmospheric stability. For the first thing we want to talk about is we want to talk about how the temperature of the air parcel changes as it goes up in the atmosphere. We also want to compare the atmospheric sounding, which is typically calculated via balloon launches twice per day. And then we also want to look at things such as where that condensation level is, where saturation is reached, how low are the cloud bases, where does the saturation occur. And then above this condensation level, where saturation is reached, we have a different type of cooling of the air parcel with height that I'll talk about. So there's a lot of interesting tidbits here when we talk about atmospheric stability. The first thing we want to start with when we talk about atmospheric stability in today's training is the term lapse rate and the stability. Now, what exactly is a lapse rate? A lapse rate is how some meteorological quantity changes over a certain distance. When we talk about atmospheric stability, we want to take a look at an air parcel, and we want to compare the air parcel's lapse rate, how quickly that air parcel cools with height. We want to compare that to the environmental surrounding air. In general, the ideal gas law assumes what's known as an adiabatic process. Now, recall from my previous training in the series that adiabatic refers to a parcel just simply rising, really no heat or energy exchange across the parcel with the surrounding environment. Adiabatic, there it is, assumes there's no net energy transfer between the air parcel and its surroundings. And there's internal temperature changes that result from the performance of work done by or upon the system. So in the case of an air parcel, this tiny little invisible bubble of air, any temperature change of a gas is going to result from the work performed by the parcel itself. And that work is primarily done via expansion of the parcel and compression of the parcel. When we talk about expansion of the parcel, that's when an air parcel rises in the atmosphere. When we talk about compression of an air parcel, that's when the parcel sinks in the atmosphere. Now, when we want to really take a look at atmospheric stability, whether we have a stable or unstable atmosphere, we want to look at the air parcel. As it rises in the vertical and the higher up above the ground in the vertical, we want to compare the air parcel's temperature with the overall environmental temperature. So as an air parcel, when it's warmer than the neighboring air parcels, is going to want to expand, because if we have a warmer parcel or just a warmer volume of air in general, a warming volume of air is going to have the molecules moving much more quickly, and these parcels are going to expand or become much further spaced apart. In that process, when you have a volume of air and these parcels within the volume, when they're warmer, they tend to be less dense, and these parcels want to rise due to what's known as positive buoyancy. The parcel's temperature is warmer and moister than the surrounding environment. So as that parcel of air rises, it continues to expand because you have external environmental air pressure decreasing with height. And as the gas in this air parcel expands, the parcel is going to perform work to continue this expansion, cooling and becoming more dense eventually. When that parcel reaches a point to where it is actually cooler and more dense than its surrounding environment, it's going to subside or sink into an environment with increasing external air pressure. Couple other important points when we talk about lapse rates, about air parcels and stability. Compression. When you compress the air column and make it shorter, the molecules become much more closely spaced together. This compression is going to perform work on the parcel similar to pushing down. If I were to push down on a plunger of an air pump, it would also result in compression. The air inside is going to warm the pump. So compression increases air parcel's internal temperature and continues until the parcel's density decreases enough to match that of the outside environment, where you get equilibrium achieved. That results in what's known as neutral buoyancy. The process, by the way, is reversible, where our air parcels can travel up and down repeatedly until reaching equilibrium. So let's take a look at a couple examples. This graphic on the right represents the differences. It kind of shows you the processes between a rising air parcel, represented by the blue up arrow, and a sinking, or an air parcel that's undergoing compression in the orange arrow pointing downward. And so if we have an air parcel, let's say that air parcel's temperature is 30 degrees Celsius. That's about 86 degrees Fahrenheit, by the way, at the surface. Let's say it's less dense than the surrounding air. It's going to have positive buoyancy. It's going to continue to rise. And then let's say at about 1 kilometer above the surface, that air parcel's temperature has now cooled 10 degrees Celsius. It's now down to 20 degrees Celsius at that 1 kilometer point. As the parcel continues to rise, you notice how much bigger the shape of this air parcel is getting. Air rising and expanding results in a much greater volume. And so by the time we get up to 2 kilometers, the air parcel's temperature is 10 degrees Celsius. This is known as the dry adiabatic lapse rate, when the air parcel's temperature decreases by 10 degrees Celsius for every kilometer rise in the atmosphere. So we started out at the surface at 30 degrees Celsius. We lost 20 degrees Celsius. It's cooled 20 degrees Celsius, the parcel, by the time it gets up to 2 kilometers. Now that's assuming that no saturation is achieved, that the parcel is just undergoing a dry adiabatic lapse rate, or cooling with height at that constant rate. On the other side, let's say now that that same air parcel at 2 kilometers begins sinking in the atmosphere, and as it sinks, it's going to gain 10 degrees Celsius for every kilometer it sinks. And so by the time, let's say we start at 10 degrees Celsius at 2 kilometers, the temperature at 1 kilometer is now warmed to 20 degrees Celsius. And as that parcel continues to sink to the surface, we gain an additional 10 degrees Celsius. So now the air temperature of the parcel is 30 degrees Celsius. So when we talk about reversible processes in the atmosphere, the adiabatic process is reversible, we are talking about the temperatures are the same at the various levels. As the air parcel expands and cools, it goes up, and compresses and warms, it goes down. So there's your major difference. In general, the temperatures remain constantly the same. That's the dry adiabatic lapse rate. Now let's take a look at atmospheric stability. Now, if you look at a stable atmosphere, you see this gentleman here. He's got a ball, and it's in this valley. Notice how he's sitting on the ball here in the valley at point A. Okay. As he tries to push this uphill, this ball, he eventually is going to get knocked down, because this parcel, represented by the letter A, or the ball, is going to move right back to the point at which it started. When we have an air parcel in the atmosphere and you try to lift it in the vertical, or it's sinking in the vertical, and it wants to return back to its starting point or its original level, that is known as a condition that's known as a stable atmosphere. Okay, and you can see what's going on here. Very stable position here at the upper left portion of the diagram that he's sitting on. That ball at point A, he tries to push it uphill, and then, of course, it's going to come back downhill under the force of gravity and come back to its original starting point. That's a stable atmosphere. If you look at the diagram here at the bottom, this portion of it, now we have parcel B, or ball B. You notice it's on top of a hill now. So once this gentleman here pushes that ball downhill, it continues to move further away from the position at which it was displaced, its starting point. It's moving further away from that. That is a condition known as unstable. Okay? So this is a good comparison to show you the difference between stable and unstable. In a stable atmosphere, an air parcel, after being displaced, is going to return back to its original starting point. In an unstable atmosphere, an initial force moves that parcel, whether we're talking downhill or up in the atmosphere, that parcel is going to continue to move away from its original starting point. That is called unstable. Now, when we talk about lapse rates and stability, we have to factor in two distinct lapse rates. One is known as the dry adiabatic lapse rate, and we'll talk about that first. The second one is going to be known as the moist adiabatic lapse rate right there. Okay, and so we'll get into a discussion on these two types of lapse rates. In addition, we'll talk about environmental lapse rate and the importance of that. All right, so for the dry adiabatic lapse rate, it's referring really to this 10 degrees Celsius per kilometer cooling of an air parcel with height, or the 10 degrees Celsius warming per kilometer as the parcel sinks. So dry adiabatic lapse rate, 10 degrees Celsius per every kilometer. The temperature is going to decrease 10 degrees Celsius for every 1 kilometer rise in height, and the temperature is going to increase for every 10 degrees Celsius for every 1 kilometer decrease in height. When we talk about sinking air, we have to talk about the process of compression, which is going to increase the air parcel's internal temperature. And this continues till the parcel's density decreases enough to match that of the outside environment, the surrounding environment. And that is going to result in a condition known as neutral buoyancy, when equilibrium is achieved between the density and temperature of the parcel compared to the temperature and density of the surrounding environment at a particular level. Again, when we talk about adiabatic lapse rates, they're reversible. Air parcels can travel up and down repeatedly until reaching equilibrium. And it is a reversible process because we start at 30 degrees Celsius at the surface for this parcel. And you go up to those 2 kilometers as we went over, and it's 10 degrees Celsius. Whether it goes up or comes down, the temperatures are the same at every level. Surface, 1 kilometer, and 2 kilometers, these temperatures are the same, so it's a reversible process. As this parcel moves, there's going to be collisions between gas molecules. And these collisions are not elastic. Each collision is going to result in dissipating heat and ultimately removing energy from the system. And this helps explain why environmental conditions are not truly adiabatic in nature. So adiabatic really doesn't have any heat energy or exchange of that energy with the surrounding environment. That's the theory behind adiabatic. But in reality, there are collisions within that given volume of an air column that occur between the gas or air molecules. And each of these collisions is going to dissipate heat and remove energy from the system. Now, the dry adiabatic lapse rate, it only is going to describe temperature changes encountered by discrete air parcels as they rise and fall, and not the average lapse rate of the atmosphere. So how do we calculate the lapse rate of the surrounding atmosphere? Let's take a look. We have to examine something known as an environmental lapse rate. This is very unique from day to day. You have different air masses moving in and out of regions. For example, and you might have varying degrees of air masses moving at various levels of the atmosphere too. So you might have a colder pocket of air, cold air advection, moving over your location, over the surface, maybe let's say between 5,000 and 10,000 feet above the ground. So you got to think again, a three-dimensional aspect of the atmosphere. It's not very wise just to pay attention to what's going on at the surface with the temperatures. Got all these different air masses coming in and out of area. We got frontal systems moving in and out of area. The various circulation patterns with high and low pressure systems in the atmosphere. This distribution of warm and cold layers of the air due to atmospheric motion. And also we have to talk about diurnal or daily heating and cooling of the earth. This produces an atmospheric profile that's going to vary over time and space. And being in the middle latitudes, United States, Europe, these air masses are moving from west to east in those prevailing westerly wind belts. We went over that three-cell theory and the global distribution of the winds, global circulation patterns in the last training series video. It's very dynamic in the middle latitudes because you have systems moving in from west to east, cooler air behind cold fronts, warmer air behind warm fronts, and again you have these large synoptic scale systems such as low and high pressure, which also tend to move in and out of the area. You can get something, by the way, that's very special condition. Normally temperature is going to decrease, you get colder with height, but in some cases you get what's known as inversions or warming temperatures with height. Environmental lapse rates are generally computed or calculated by launching weather balloons and retrieving data such as temperature and moisture. And these weather balloons kind of connect to this mini raw wind sound system. As the balloon goes up with a transmitter attached around its neck, as it goes up in the atmosphere, it is going to constantly be feeding that mini raw wind sound system, that computer on the ground, various atmospheric data as the balloon rises, such as temperature, humidity, the wind direction and height, or the wind direction and speed with height. All this data is very important in determining the environmental lapse rate and what's going on with height. Are my winds veering with height? Are my winds backing with height? When you look at severe weather, severe thunderstorms, one of the main ingredients of severe thunderstorms is what's known as wind shear, whether that be major speed differences in the vertical or wind direction changes, drastic wind direction changes in the vertical. These weather balloon launches are going to give that data. When we talk about stability of the atmosphere, balloons are launched twice a day from select locations. They are going to give this environmental lapse rate. All right, so we talked about the dry adiabatic lapse rate, the environmental lapse rate. Now let's talk and turn our attention to the moist adiabatic lapse rate. Moisture exists in the atmosphere as a gas, and most of the time this gas is going to be referred to as water vapor. Sufficient adiabatic cooling of an air parcel, it's going to lower the temperature of its water vapor to the condensation point. So as an air parcel rises, it initially rises at an unsaturated adiabatic lapse rate or a dry adiabatic lapse rate. Once the air parcel, as it cools, as it rises and cools, it expands, and the pressure or density as well as the temperature is equal to, let's say the temperature is cooling to the dew point where we reach saturation. What's going to happen is you'll end up getting a cloud layer to develop as the water vapor is converted to a liquid via the process of condensation, and you get the formation of clouds. Above that saturation point, that air parcel is going to continue to rise. However, it's going to now cool at a much slower rate because as saturation is achieved and as a water vapor is converted over to liquid water in the formation of the cloud, that releases heat to the surrounding atmosphere. So we have that release of heat slowing or offsetting the cooling process of the air parcel. That's going to result in a moist adiabatic lapse rate that's actually less than the dry adiabatic lapse rate. The moist adiabatic lapse rate being 6 degrees Celsius for every kilometer. Remember, the dry adiabatic lapse rate was 10 degrees Celsius for every kilometer. So the process of saturation, the conversion of the release of latent heat or hidden heat to the surrounding air as saturation is reached, is the main reason why your moist adiabatic lapse rate, a saturated parcel, is going to cool at a lesser rate with every kilometer in height as compared to a dry or unsaturated air parcel. The condensation point is the temperature where the air parcel is equal to the dew point, where you get 100% relative humidity. The parcel can no longer contain any more water vapor at that point, with the temperature and dew point being the same as I discussed. Cooling beyond this point, the saturation point or condensation point, is going to force some of the water vapor out of the parcel in the form of liquid water. And anytime we have any kind of conversion of a gas to a liquid to a solid, you can even go from a gas all the way over to a solid without going through a liquid state, you are going to have some sort of energy either absorbed or released to the surrounding atmosphere. Now, when water molecules, when heated beyond that saturation point or condensation point, they're going to change phase and become water vapor, and that water vapor is absorbing and storing heat as potential energy until completion of a phase change, conversion of a liquid water to a water vapor. So initially, let's just use an example here. We have the sun shining on one particular day, sun's out. The incoming solar radiation is heating a water surface. That heating of the water surface results in the conversion of a liquid water. Let's just say the sun's heating a lake. All right, that's internal incoming solar radiation is going to evaporate some of that liquid water into a vapor. And that water vapor is actually going to absorb and store heat. And it's going to be considered potential energy. That potential energy is then released upon a phase change from the water vapor to a liquid. It's called a latent heat of condensation. It's a very important process when we talk about the development of what are known as towering cumulus or hot towers when we talk about a tropical system. But in general, that heat is going to be released. So it's a case of, in a phase change from a liquid to a vapor, we're gaining heat and storing the heat. From a vapor to a liquid, we're then returning the heat back to the surrounding atmosphere. And that goes on throughout all the phase changes. And I'll show you an example of the phase changes here in a moment. The condensation, or water vapor forming to a liquid water, is going to reverse the above phase. It reconverts potential energy stored by water vapor molecules into energy of motion or kinetic energy. Again, that is referred to as latent heat of condensation. Now, this potential energy conversion releases heat into the atmosphere, altering the adiabatic process in moist air parcels once condensation occurs. That, again, is the primary reason why the moist adiabatic lapse rate is only 6 degrees Celsius per kilometer compared to the dry adiabatic lapse rate, which is at 10 degrees Celsius per kilometer. The release of heat to the surrounding atmosphere results in the moist adiabatic lapse rate, there it is, which is 6 degrees Celsius per kilometer, rise in elevation. It's going to be much less, the rate is much less or lower than the dry adiabatic lapse rate. Release of latent heat of condensation will manifest itself when air parcels subside as well, which they do so at the dry adiabatic lapse rate, regardless of moisture content. So that would result in a increase of 10 degrees Celsius for every kilometer the air parcel subsides or sinks. Now, air parcels can rise dry adiabatically initially until condensation results, liberating that latent heat to the surrounding air. Then the parcels rise at the moist adiabatic lapse rate until the equilibrium is achieved. A good example of this is on a hot summer day. Again, the Earth's surface is, let's say the sun is out, the Earth's surface is being heated. Initially, the air parcel is going to rise at the dry adiabatic lapse rate. And then let's say the cloud base of a cumulus cloud on a hot summer day is at 2,000 feet above the ground level of AGL. So you know between the surface and 2,000 feet, where you see that cloud base, where it's located, that parcel is going to rise to the dry adiabatic lapse rate, 10 degrees Celsius cooling for every kilometer it goes up in the atmosphere. Okay? But above 2,000 feet, that parcel is going to change its rate of cooling. It's now going to cool above the cloud base, above that point in saturation. It's going to cool now at the moist adiabatic lapse rate, above the cloud base, 6 degrees Celsius for every kilometer rise. And one other important point to make here is air masses that experience orographic lifting or lifting forced by mountainous terrain, they tend to warm significantly on the lee side of the mountains. And a great example of this is the predominant westerly wind flow up against a north-south oriented mountain range such as the Rocky Mountains, where you get tremendous warming on the lee side of the Rockies. In fact, they have a condition where you may have a ton of snow on the lee side of the Rockies, but you get an adiabatic sinking air motion on the lee side of the Rockies, and it's called a Chinook. And it's a word, it's basically a word kind of depicts snow eater, because the snow disappears so fast. The temperatures change so quickly to milder air as the air sinks, the air parcel sinks down the lee side of the Rockies. Just a great example. All right, so here is a look again at our diagram. On the left, showing you the dry adiabatic lapse rate. We kind of hit this already earlier in the training on the previous diagram I showed. But in general, just showing as air rises, it cools, expands. Initially, it may cool and rise at the dry adiabatic lapse rate, 10 degrees Celsius for every kilometer. And then it compresses at the same when we talk about a dry adiabatic lapse rate, okay? But then, if you look over here on the right side, now we're going to factor in, we're going to take a look at the difference between the dry adiabatic lapse rate from the surface to 1 kilometer. This is 1 kilometer at this point. So let's say we'll compare this dry adiabatic lapse rate to the moist adiabatic lapse rate, okay? So in these cases, let's start off with this left side of the diagram. We have a temperature of 20 degrees Celsius, which is about 68 degrees Fahrenheit. We got a dew point temperature at 0 degrees Celsius, 32 Fahrenheit. So the temperature and dew point are farther apart initially with the air parcel on the left. Now, as the parcel rises in the atmosphere, it's going to cool at the dry adiabatic lapse rate because the air is far from saturation. 20 degrees Celsius temperature, a 0 degrees Celsius dew point. We got a 20 degrees Celsius spread between temperature and dew point. The atmosphere is very dry. As the air parcel rises up to 1 kilometer, the temperature is going to be 10 degrees Celsius at this point because it's cooling at the dry adiabatic lapse rate of 10 degrees Celsius per every kilometer rise in the atmosphere. And now the dew point is at negative 2 degrees Celsius. So it is starting to become more and more moist. The temperature dew point spread now is only 12 degrees Celsius at 1 kilometer on the left-hand side here with the dry adiabatic lapse rate. So this parcel will continue to rise again at the dry adiabatic lapse rate because we haven't reached saturation yet. Now the graphic on the right, we have a different case, a different scenario entirely. We have a temperature of the air parcel at 20 degrees Celsius, and we have the dew point at 20 degrees Celsius. So the atmosphere is already saturated. So right away, this air parcel is going to rise at the moist adiabatic lapse rate of 6 degrees Celsius, cooling with every 1 kilometer rise in the atmosphere. And sure enough, look at what the temperature is up at 1 kilometer. It's 14 degrees Celsius. And the dew point also matches the temperature at 14 degrees Celsius. So we have a saturated air parcel rising here on the right. And as this air parcel rises, saturation is achieved. Don't forget, 6 degrees Celsius per kilometer for the lapse rate, the moist adiabatic lapse rate here on the right. And that's mainly caused by latent heat being released as water vapor is converted over to a liquid water. In fact, this conversion process releases 600 calories per gram of heat energy to the surrounding air. Just wanted to point that out. So you can see there's a big difference in where your air parcel's temperature is going to be based on the rate, the lapse rate at which this air parcel rises. As promised, I wanted to show you water phase changes and the importance of these water phase changes in the atmosphere. Right, so on the left, we have a case where we have a block of ice at 0 degrees Celsius at the freezing point. By the way, the blue arrows, as we go to the right here at the top of the diagram, this is resulting in a cooling process of the surrounding environment. This is a case where heat energy is actually absorbed or taken away from the surrounding environment. So you take heat energy away from the surrounding environment during these phase changes, it's going to cool the surrounding air. The bottom shows these red arrows kind of going from right to left. Just showing you that heat energy is actually released to the surrounding environment. Okay. Now, on the left here, we have an ice, 1 gram of ice at 0 degrees Celsius at the freezing point. In the middle here, we have the liquid water droplets. And in the far right, this would be water vapor in gaseous form. Water in gaseous form known as water vapor. Okay. So, if we work our way, if we wanted to convert from ice, a solid, to a liquid, we would have what's known as latent heat of melting. And in this case, we'd have 80 calories of heat energy would be absorbed by this ice cube. And in order to do that, when energy is absorbed, heat energy is absorbed by the solid, it's eventually going to melt. The rigid structure of these molecules will become less organized, and it will convert to a liquid. So now let's keep following this diagram from left to right at the top. If we have 1 gram of water, let's just say we have 1 gram of water, and then we want to convert that gram of water over to, let's go from a liquid, let's actually go to this point here. We'll go from a liquid over to water vapor. When liquid is converted to a water vapor, okay, latent heat of vaporization occurs, and you're dealing with 540 calories of heat energy being absorbed by the water droplet. All right, that's going to cool the surrounding environment. I want you to think about this. When you're sweating in the summer, you have all these liquid water droplets on your skin. That's the sweat. And as the sun heats that sweat, right, it evaporates some of that sweat off your skin, and evaporation is actually a cooling process to your skin. The same thing's happening here when we convert from a liquid droplet to water vapor. That droplet of water is absorbing a lot of heat energy to basically result in these molecules moving much more quickly and expanding and moving and changing into a form of a water vapor. Now, what happens when we go from a water vapor and we want to convert to a liquid? That's that latent heat of condensation I referred to earlier. And so we have 1 gram of water vapor at 100 degrees Celsius, and it is converting over to liquid. This is going to result in the release of 540 calories of heat energy to the surrounding environment. It's going to form this liquid. Now, what happens if we go from a liquid back to a solid? Okay, liquid to a solid, it's known as a latent heat of freezing. And 80 calories of heat energy is released by this water droplet to the surrounding air, and that is then going to allow that water to convert to a solid ice. So there's a lot of calories, heat calories involved in these phase change processes in the atmosphere. Of course, water exists in 3 phases in the atmosphere: as a water vapor, invisible gas, as a liquid water, as well as a solid. There's also cases, deposition, as well as another type of situation where you actually go from a solid to a vapor directly without going through a liquid phase, and then from a vapor back to a solid without going through a liquid phase. And that involves even more energy between those phase changes. All right, so now getting back more to why is determining these lapse rates and stability so important. To determine atmospheric stability, we compare the air parcel temperature to that in the environmental temperature. That's going to be computed the environmental temperature via the weather balloon launch. If the air parcel's temperature is warmer, that air parcel is going to be less dense. If it's warmer than the surrounding environmental temperature, the parcel will be positively buoyant and continue to rise. And this is an example of an unstable atmosphere. Vertical development of cumuliform clouds is likely when you have an unstable atmosphere. And if the air parcel's temperature is colder or more dense than the environmental temperature, on the other hand, the parcel will tend to be negatively buoyant and sink, and this is an example of a stable atmosphere. And with a stable atmosphere, you tend to see more of those layered stratiform clouds in the sky, horizontal spreading of clouds. All right, so we talked about positive buoyancy. Air parcel's temperature is warmer or less dense than the surrounding environmental temperature. We talked about negative buoyancy, where the air parcel's temperature is colder and more dense than the surrounding environmental temperature. Now let's talk about neutral buoyancy. This occurs when an air parcel reaches equilibrium with the surrounding environmental air. The air parcel's temperature is going to be equal to the environmental temperature. And in this case, when we have neutral buoyancy, the air parcel will neither rise nor sink. And so what we do when we determine atmospheric stability is we compare the air parcel's temperature to the environmental temperature at various levels vertically in the atmosphere. Now keep in mind that the cooling rate of an air parcel will change as it rises in the atmosphere. We talked about how it would first start rising at the dry adiabatic lapse rate, the DALR, and then once condensation occurs, you reach saturation, temperature, and dew point are the same. Latent heat is going to be released, that latent heat of condensation, to the surrounding atmosphere. It's going to offset the cooling process, and the air parcel will then cool more slowly at the moist adiabatic lapse rate. All right, and I believe this is the last. Yeah, I'm down to my last couple slides here in tonight's training. Let's just summarize things nicely here with this particular graphic. Okay, atmospheric stability in general. Generally, we have an unstable atmosphere when a parcel, the temperature of the parcel is greater than the environmental air around it. So basically what I'm saying is the parcel's temperature is warmer than its surroundings. It rises and expands. It continues to rise and expand. That is a case known as instability in the atmosphere, unstable conditions. Parcel's temperature is greater or warmer than the surrounding air. The second case we have is a stable atmosphere when the parcel's temperature is lower or less than the surrounding environmental air temperature. And so in this case, the parcel in a stable situation is going to want to sink and compress. And then neutral stability occurs when the parcel's temperature is equal to the environmental air temperature. So basically the parcel will not rise nor sink in this case. Here is the example of the diagram once again. If I were to compare these different colored circular shapes, and we call these air parcels, an unstable situation would occur at this point if any kind of force were to move this air parcel would continue moving away downhill from its original starting point. This is a case of unstable atmosphere. Now let's say we have an air parcel sitting in this valley. If we try to push that parcel uphill, it's going to want to return to its original starting point. That's an example of stable atmosphere, returning to its original starting point after a parcel is forced to move. And then neutral stability. Notice this flat gradient here, this flat surface. In general, this is not going to want to move at all, this parcel in this case. Okay, so just some good comparisons here. This is a great summation of tonight's training, comparing parcel temperature to surrounding air or environmental temperature. And then one other thing I want to point out, if you can have a condition in the atmosphere where it's called conditional instability, or when things are conditionally unstable. And basically, if the parcel rises at a dry adiabatic lapse rate, it's always going to be colder than the environmental surrounding air. This is a condition known as stable, right? Absolutely stable. When an air parcel tends to rise, let's say it rises at the moist adiabatic lapse rate, it could actually result in a condition known as absolute unstable or absolute instability. So conditionally unstable refers to whether a parcel of air is rising at the dry adiabatic lapse rate. If it's rising at the dry adiabatic lapse rate, the parcel is absolutely stable. But if it's rising at the moist adiabatic lapse rate, the parcel is absolutely unstable. And it all has to do with that parcel's air temperature compared to the surrounding environmental air temperature at successive levels in the atmosphere. If that parcel temperature is warmer than the air temperature, the environmental air temperature around it, it's greater than or warmer than, it's going to continue to rise, we have instability. If the air parcel temperature, again, is less than or colder than the surrounding environmental air temperature, we have absolute stability. And if they're the same, it's neutral stability. Here is a look in the atmosphere between atmospheric instability, unstable conditions, and atmospheric stability, stable conditions. So this is unstable atmosphere on the left. Look at this nice cumulonimbus cloud. Look at the anvil shape at the top of this cloud. These clouds around it too are also rising vertically, indicating instability in the atmosphere. When you see these puffy clouds like this, it's a day in which the atmosphere is unstable. That air parcel, as it rises, is going to be warmer than the surrounding environmental temperature and want to continue to rise. And by the way, the level of moisture in that parcel also matters. A moist air parcel tends to be less dense than a dry air parcel. So moist air parcels want to tend to rise and be positively buoyant as well. And then on the right here, notice this dull gray layer-like cloud structure in the sky on this particular day, and that indicates atmospheric stability. This is a case where air parcel rises, and the air parcel's temperature at various levels in the vertical are colder than the surrounding environmental air, so that parcel wants to sink. So in general, this is a stable-looking atmosphere when you see these layered clouds. This is an unstable situation, especially occurring during summertime. All right, that wraps the training up tonight. I really hope you got something great. Hopefully these explanations really help explain how the weather works. Tonight was a very important topic, and when we talk about atmospheric stability, that means a lot for our weather here at the Earth's surface. Whether we see thunderstorms or whether we see continuous rain or snow from stratus-type clouds, stability really does matter, okay? And in future training, soon we'll be getting into what's known as a skew-T log P diagram. And a skew-T log P diagram is a thermodynamic diagram. It's a very important diagram to really understand the different saturation levels in the atmosphere. Will a parcel rise at the dry or moist adiabatic lapse rate? It gives us a lot of clues of the wind direction and speed with height. Whether I have warm or cold air advection occurring, I can look at a skew-T diagram and know that. And so tonight's introduction was on atmospheric stability, comparing air parcels to surrounding environmental air at various levels. And I really hope you got a lot out of tonight's training. Just keep in mind that as the air parcel rises, it's going to cool, it's going to expand. And as the air parcel sinks, it's going to compress, undergo warming as it sinks and dry out. All right? Thank you so much for watching. Thank you so much for subscribing to the Spot on Weather YouTube channel. Till the next training session, still plenty more that I have in the queue to provide. So I'm looking forward, again, as we move through the month of May and through the summer months. By the way, happy Mother's Day out there to all you mothers as well. I definitely want to put that out there since it is Mother's Day. All right, take care, everybody. Until next time, God bless and take care.